All right, lesson 1-1, day 1. I'll let you go ahead and read here the overview. And then we have our objectives. And today we're going to focus mostly on the first one up here, which is to set up models to represent real-world phenomena, numerical, algebraic, and graphical. So a mathematical model is a mathematical structure, graph, equation, table, etc., that approximates real-world phenomena in order for us to study it or predict future behavior. That's what we want to do with math. We want to be able to say, this is the trend that we see, and this is what we believe will happen in the future. And as it says, often the best insight can be gained by using a variety of models to analyze a situation. First off, we talk about numerical models, and numerical models are just ones in which we look at the numbers or the data and we analyze those as we go. So this one says we're going to track the minimum wage. The numbers in table 1-1 show the growth of the minimum hourly wage, MHW, from 1955 to 2005. The table also shows the MHW adjusted to the purchasing power of $1996. What that really means is they're adjusting it for inflation. So they're using the consumer price index to adjust that for inflation. That tells us how much you can buy with the money that you have. And it says answer the following questions using only the data in the table. And A is, in what 5-year period did the actual minimum hourly wage increase the most? Well, from 75 cents to $1 is 25 cents. So we're just looking at the minimum hourly wage because that's what they asked about. From $1 to $1.25 is 25 cents. From 25 cents to 60 cents is 35 cents. So they finally got a little increase there. That is really thick and hard to read. All right. And then we got from $1.60 to $2.10, hey, that's a whopping 50 cents. $2.10 to $3.10 is $1. That's even more. $3.10 to 35, back down to 25 cents. $3.35 to $3.80 is going to be 45 cents. And then we have $3.80 to $4.25, another 45-cent increase. $4.25 to $5.15, almost $1. That's 90 cents. And then $5.15 to $5.15, nothing. Absolutely nothing. So in what 5-year period did the actual minimum hourly wage increase the most? Well, that would be from $2.10 to $3.10, so 1975 to 1980. So really, like I said, just reading the graph is what we're doing. And then B says, in what year did a worker earning the minimum hourly wage enjoy the greatest purchasing power? Well, that's these numbers over here. And so we take a look and we see $6.47 in 1970. That was when they had the greatest purchasing power. Kind of strange to think when you look at that and see that the minimum hourly wage was $1.60. So a worker on minimum wage in 1980 was earning nearly twice as much as somebody in 1970. So here to here. $1.60 to $3.10. Yeah, $3.20 would have been double, so they had a big increase there. It says, yet there was great pressure to raise the minimum wage again. Why? Look at the purchasing power. Because of inflation, they actually were able to purchase, I need to go one more down here, less than 1970, and that's because of inflation. So the purchasing power had dropped due to inflation. And in fact, if you go back in history, you find out that the 1980s had a very severe recession. Some people call it a mini depression that went on in the 80s, and that's the reason that inflation was so high. So even though they were making more money, they were able to purchase less with that money. And that's why there was an argument there for the increase of the minimum wage. Now, when we get to table 1-2, this shows the growth of the number of prisoners incarcerated in state and federal prisons at year's end for selected years between 1980 and 2005. And we want to know, is the proportion of female prisoners increasing over the years? So we start to think proportion. proportion. That means dividing. Well, dividing with this set of numbers, we could get percentages. And most people understand percentages, so that's what we want to do. So in our graphing calculator, we're going to use that Stats Edit button. And what we'll do is we will put the years since 1980 in list 1, which means instead of 1980, 1985, we'll use 0, 5, 10, 15, 20, and 25. That'll just make it a little easier to punch things in. And now, there'll probably be a little pause in the video because I remembered that I needed to turn the recorder on at this point. So with this one, I'm going to go back and get rid of my slip of the finger there. There we go. Now those match up. And now in list 3, they want the total. And the good news is the total is already up here, so we could use that. You can actually use the graphing calculator as a spreadsheet, but I'll show you how to do that in a second. Like I said, the best proportion to use for this would be percentage. Everybody understands percentages, so that'll make this easy to do. Now, we're going to use our graphing calculator as a spreadsheet. And what I mean by that is we're going to allow it to do some calculations for us. So we're going to go to list 4, and we're going to go arrow up. So we move that cursor up to the name of the list, and then we tell it what we want it to do. And what we want it to do is give us percentages. So we're going to take 100 times, and then we're going to use parentheses and tell it the list names. Now, to get the list names, you have to hit second, and then, like for list 2, it'll be second number 2, and for list 3, it'll be second number 3. So second L2, comma, second number 3, parentheses. And when we hit enter, it's just going to fill that column for us. It does all the math. We don't have to do it.
Where's the comma button?
The comma button, oh, right above the 7. Everybody got it all in? Uh-oh. So I must have hit that comma again when I was talking to Max. Oh, that's right. We're not listing those. Yep, divide. Thank you. I was looking over there and saying that was a comma. There we go. So those are the percentages. And their question is that proportion increasing over the years? Well, 3.95, 4.58. Uh-oh. Yes and no, right? Yes and no, right? Yours is different because I think I slipped on another one.
Yeah.
Thank you. Transposed. Good gravy. Also 3. There. So even this one with still the 6s, there's still a little percentage increase in here. So from this chart, they're blaming a little bit of this on the increase in the females. That's what they're doing. So is the proportion of female prisoners increasing over the years? Yes. But we probably want to, especially on an AP exam, we'd want to be a little more detailed. We would say it increased in the following manner. %3.951% to 4.582% to 5.685% to 6.044% to 6.686% to 7.077%. Notice we're given specifics here. We're saying, yep, this is what we saw. They can't see our graphing calculator when they grade our AP exam, so we want to make sure that we're showing them everything that we see as we go through there. So with these, it was just looking at the data. Like I said, you're kind of using your graphing calculator as a spreadsheet. In fact, at this point, most tables are not going to give you the total. So what we could have done was have the graphing calculator actually do the addition of those two at one time and get the total on the graphing calculator. We could just put the female stuff in for list 2, the male stuff in for list 3, and then for list 4, tell the calculator to add those two lists together. So as long as you arrow all the way up, you could tell the calculator to do anything in top of that command center up there, which would be wherever those list names are. So we can use the calculator to do a lot of stuff that usually we'd say, hey, we've got to do this by hand. Now, we probably want to save this data for example 5. So when we put some more stuff in here, let's try not to go over the top of what we already have. Chances are pretty good we're going to get to example 5 today, so let's just make sure we store that stuff in there and don't mess with it. Algebraic models. Algebraic models say, here's what we saw with the math. Now, here's an equation that we can use that will work with it. So algebraic models use formulas to relate variable quantities being studied. One benefit of an algebraic model is that it can be used to find unknown quantities by relating them to known ones. So, comparing pizzas. Sounds like something people would do. A pizzeria sells a rectangular 18 by 24 inch pizza. Okay, 18 inches by 24 inch pizza. And they sell it for the same price as a large round pizza, which has a 24-inch diameter. That's the really important piece here, is that the diameter is given to us. All right, if both pizzas are of the same thickness, which option gives the most pizza for the money? So normally we'd say with something like this, we should think in 3 dimensions, but they're saying it has the same thickness. So we don't need to worry about that. What we need to worry about is the toppings on the top, you know? And that's not 1-dimensional, that's 2-dimensional. So we need to do 2-dimensional math here, which is for rectangles, area equals length times width. For circles, pi r squared. And whichever one gives us the bigger area is going to be the better by. So over here, we'll just take 18 times 24 to get our area. And we get 432 square inches. On the other side, we recognize, okay, they're baiting us with the 24. We really need a 12 in there for r. So it's going to be 12 squared times pi, and we do have a pi button on the calculator. So 452.389 square inches. So which one gives you more pizza for the buck? The round one. The round one. So if both options are available, buy the round pizza. It has that higher area that we would want. And both of them are the same cost. And that's not the issue here. The issue is which one will give us more pizza. So now, we need to start designing an algebraic model, designing an equation that's going to work for us here. This says we have a department store that's having a sale in which everything is discounted 25% off the market price. The discount is taken at the sales counter, and then a state sales tax of 6.5% and a local sales tax of 5% are added on. So what's the total tax? 7%, yeah. So that's what we care about in the end. You know, it's not like they calculate those two separately. They do when they're paying the money into the government, but for us, they just say, hey, it's going to be 7% sales tax here. The discounted price D is related to the marked price M by this little formula D equals K where K is a certain constant. What is K? Here's what they're asking us. If we're not paying 25%, we care about what we are paying. So if we're not paying 25%, how much are we paying? 75%. So if you had a calculator in the store, instead of figuring out 25% and then subtracting, you could just figure out 75% times the market price. Now that, of course, is before tax. In Minnesota, we're not used to clothes being taxed, but some states do tax clothing. So number 2 says the actual sale price S is related to the discounted price D by the formula S equals D plus TD, where T is a constant related to the total sales tax. What is T? Boy, did they make this sound hard. This is, what formula would we need if we don't just want to look at the overall, or the price of just the clothes, if we also want to look at the tax? So what we would have to do is say, all right, we know that we're going to pay 75% of whatever the market price is for this thing. But in addition to that, yeah, we have to do the tax. So what should we put in there for the tax? 0.07. Because with decimals, remember, percents always have to move those 2 decimals there. So what this means is we actually could go a little bit further here. I mean, we can keep doing the multiplication and we can get a better formula. I don't leave myself enough space here for that. So if we take our little 0.07 times 0.75, we get this. And we notice, hey, they both have an M on them. Maybe I can take this down to 1 step if I have a calculator in the store and just add that together. So now if we grab an item and we have a calculator in the store, we can just take the price that's on the tag times 0.8025 and we'll know exactly what we're supposed to pay when we go up to the register. So 3 says if we use those steps, all the things that we just found out from 1 and 2, we can find a constant P that relates S directly to M with the formula S equals PM. Okay, they've made this sound difficult again. So what they're saying is, when you're at the store, what are you going to multiply the market price by? This. All of this goes back to, do you remember talking about direct variation? Does that sound familiar? Remember direct variation? Direct variation is too easy. We forget it because it's too easy. Direct variation is just when you're multiplying 2 things to get an answer. For instance, if you go to the movie theater and it says $7 for everybody all the time, well, a formula to get the ticket price would be 7 times X. If you know how many tickets you want to buy, you take it times 7 and you get a number. So this is explaining that we can start with something that looks a little complicated and we can get down to something very basic that's just going to use direct variation. And so they're taking us through those steps. So the question is, you went into the store, you've got $30 to spend. Can you buy a shirt that's $36.99? Well, like I said, you probably want a calculator in the store. But we already know, when all is said and done, we're really just taking 80.25% of that cost. So we need that little 0.8025 times $36.99. And that will be $29.68. So if we answer the question, are we going to be able to take that shirt home? Yep. We have $30. We can do it. There it is. Number 5 says, if you have a credit card, but you're determined to spend no more than $100, what would be the maximum total value of your marked purchases before you present them at the sales counter? So now we're saying our answer needs to be 100. Well, that's not too hard either. All we have to do is divide. So we're going to take 100 and divide it by 0.8025. And we would always round down. The store won't. The store will always round up. So we won't be able to afford this if we round up. So we're going to put $124.61. Even though this one would already round down, even if it said 124.66 or 0.616, we would still keep it 124.61. Because again, our limit is $100. And this is what we have to stick to. So that, like it says, is designing an algebraic model, but one that maybe we don't need a calculator and all kinds of stats buttons for when we think about it. So a lot of blah, blah, blah here. It says, the ability to generate numbers from formulas makes an algebraic model far more useful as a predictor of behavior than a numerical model. So if you want to know something about, 5 years from now, what will natural gas prices be? You'd like to have an equation. That'll make it nice and easy. Indeed, one optimistic goal of scientists and mathematicians when modeling phenomena is to fit an algebraic model to numerical data, and then, even more optimistically, to analyze why it works. Sit and say, is this a good one? Is this a bad one? How do we know? For example, nobody has ever devised a successful formula for predicting the ups and downs of the stock market as a function of time. Although that does not stop investors from trying. That's what they do. That's their job. They try to guess what's going to happen with the stock market. If numerical data do behave reasonably enough to suggest that an algebraic model might be found, it's often helpful to look at a picture first. So that brings us to graphical models. So graphical model, visual representation, taking a look at the data. And what we're doing when we make these graphical models is we're trying to see, do they look like they line up kind of in a straight line? So we can use a line for a model of this. Do they look like maybe a parabola? So we can maybe use a parabola to model what's going on here. And that type of model can give insight into the relationship between the variable quantities. Because like I said, if we can see the shape, we can think, what have I done in math before that would give me that shape? How am I going to get that information? So visualizing Galileo's gravity experiments. Galileo Galilei, from 1564 to 1642, spent a good deal of time rolling balls down inclined planes. So basically he had a board, and he inclined it, and he dropped the ball, and he would check and see, how much time does it take for this to hit the other end. And he recorded that along with the distance traveled. So he recorded all of this stuff, and his experiments are commonly repeated in physics classes today, so easy to reproduce this data. It's something that just happens. So if you graph these points, you get this. And it says, what graphical model fits the data? So it's not just what do we see and what's the shape, but can we get an actual model for this data? Now, if you're thinking line, I would say, actually, if I were to just connect these up, it looks much more like a smooth curve than it does like a line. Not that a line wouldn't be a horrible predictor, but it definitely looks like a smooth curve, and that looks like the right side of a parabola. So I would be thinking we should do something with y equals x squared, which is, of course, called a quadratic. Well, the good news is our graphing calculator does all kinds of regression, including quadratic regression. The bad news is we want to keep that data that we had in there where it was. So stats edit, and now we're going to go use list 5 and list 6, bless you. And we're going to go ahead and put in the 0 through 8. For list 5. And then for list 6, put in the rest of the data, which will be the distance traveled, and hopefully I won't transpose any numbers this time. Now normally, you guys have done linear regression before. That's an Algebra 2 thing where you do linear regression. But we're not going to do linear regression. We're going to do quadratic regression. And what we need to remember is the two lists we are using are list 5 and list 6. So stats, calculate, once over to the right. And then we want quadratic regression, which is right down here, number 5. And we have to tell the calculator, and I know there's going to be a couple of different looks. Some of you have the ones that say like store frequency and all of that good stuff. Wherever we see list 1, we're going to want to put list 5. And remember, you just hit second, and the name will show up. And then go down to the next list, and you want to put list 6. I'm going to have to put comma list 6 on mine. And no, I'm not going to teach you store frequency today. We'll do that another time. This one will be a little basic. And you go all the way down to calculate once you've changed those lists to list 5 and list 6, and then hit enter. Zero and 75. 6.75. 37, 36.75, and 48. Line regression. Stats, calculate, number 5, not 4. There we go. And what I was thinking is I have to walk around now because some of you have different screens. All right, so list 5 there, list 6 there, all the way down to calculate. Stats. Let's see, calculate. Oops, it's second. 6 is number 5. And then we need to do second 5. Yes, it's saying the same. All right. So if we get this in here, this is telling us if we use that quadratic model, then all we have to do is put 0.75 in here. And that will be a perfect fit. Now, what we're going to do is we're going to see it. We're going to make sure. So when you're doing things in stats and you want to see it, you have to use stat plots. We have to hit second, y equals, and we have to go into any one of them. It doesn't matter. I'll just go into number 1. And while Blinky is on top of on, we're going to hit enter there. So we're turning it on. And when we move away from that by using the arrows, we can see that on is still blackened. So that means it's been turned on. And we do just want to see dots right now, so that's just fine. But we changed the lists. So we have to hit second 5, and then arrow down, and second 6, because we wanted to save that other data. And we also have to change our window, because our window was from -10 to 10, and that doesn't make any sense with the data we have up here. We have 0 to 8 for our x's, so maybe -1 to 9. And we have 0 to 48, so maybe -1 to 50 for our y's. And if we hit graph, we should be able to see nice little dots. And the other thing you're seeing is something from Algebra 2. So give it a second here. We did quadratics in Algebra 2. So we're seeing the same thing they have up here. But what I want to know is how good a fit is that little 0.75. So I'll go back into y equals, and I'll just type it in. 0.75x squared. And I want to see it graphed right over the top of that other data. It's pretty doggone good. Now, some of you that have the newer calculators, you got a little thing that said R equals, and it probably said R equals 1, didn't it? A value of R, which is the correlation coefficient of 1, means it was a perfect fit. Now, those of us that don't have it on, I'm going to show you that tomorrow. We'll go ahead and put that in tomorrow's stuff, and we'll watch what happens when you're doing the correlation coefficient. So this says, what graphical model fits the data? We've got it right here. And we did find a model that fits. In fact, it fits perfectly. It's exactly what we wanted. So down here at the bottom, it says this insight, and this is kind of, well, it's ironic because Galileo is the one that came up with all of this data, but they didn't start doing a lot of math with it until calculus. So all of these got named after Isaac Newton, even though Galileo was the one who had done all of the studies. So when you do Newton's calculus, you're going to see, hey, this data actually is from Galileo. So on the next page, we already have this data in. I think we can make it happen. What we want to do is fit a curve to the data. We showed in example 2 that the percentage of females in the U.S. prison population has been steadily growing over the years. Model this growth graphically and use the graphical model to suggest an algebraic model. So what I'm going to do is I'm going to go take out Galileo's stuff. Stats, edit, and I'm just going to go up to list 5 and list 6 and clear that stuff out because we don't need that anymore. And what we want to do is take a look at the data that we have here. So this says model this growth graphically and use the graphical model to suggest an algebraic model. So we're going to make a scatter plot using the list that we had in list 1 and list 4 from example 2. So that means we're going to go back into our stat plots, and we still want it turned on, but we're going to go down here and tell it that we want that list 1 and list 4. And that also means we're going to have to change our label. Because list 1 for the prison population, we had used years 0, 5, 10, 15, 20, 25. So window, maybe -1 to 30. And our Y values were percentages, and what we had seen so far were pretty small percentages. So maybe we'll just do 0 to 10%. I still have my 0.75x squared in there, so I'll take that out of y equals. So there's the data. We still had our x squared in there. Go to y equals and clear that one out because that was part of that last Galileo's experiment that we did too. It should just be dots right now of the female prison population data. Sure. Because we did 0 to 25 years, and then our percentages so far were pretty small.
It says
Oh, okay, yeah. No, we had multiplied by 100 for that one. All right, looks like that. Do you think a line would be pretty good for that? Line fit that? Okay, not awful, but, you know, a line. So we go back in, and we tell them we're going to put -1 to 30 and -1 to 10 in there. And yeah, it's probably not going to be a perfect fit, but it does look like it's linear. It looks like we could get a line that would be a pretty good line of best fit there. Now, we can do it by hand, but we're not going to. We've got all this good stuff in the calculator right now. So stats. Calculate again, but this time the one I wanted to push before, which is linear regression, number 4. And we want it to use the 2 lists that we have just looked at, which are list 1 and list 4. And again, some of you have a different screen, but all you're going to do is change those to list 1 and list 4. And that gives us this equation. So now, if we want to see that, we're going to go into y equals and punch that in to see just how good a line of best fit it is. Again, not going to be perfect. Big breath. Not too bad though, is it? It's not awful. You know, it's not perfect, but it's not awful. And do know that we absolutely could do this by hand. We could just take a couple of points that we have and we could find the slope and then put it into point slope formula. We've done that again and again, but the calculator is more accurate. So, you know, we probably use the calculator for this one to get that linear piece. And these boxes were just for exactly what I'm showing you up there on the graphic calculator of what we went through and what we did. Okay? And that's what we can get through today. So we'll start with that exploration down there at the bottom, which means you can't have a lot of homework. I mean, we're just talking about some modeling right now, so this is going to seem like kind of a lame assignment, but getting you back into just looking at data and tables. And remember, we're not going to do stats calculate for all of these. For some of these, you just look at the tables and you say, this is what I see from the tables.
Should we do graph paper for that assignment possibly, or?
You might want it. You might want it. A lot of the stuff, like I said, we're not necessarily going to do by hand. We'll use the graphic calculator for. But especially if you want to look at it to see, should I use a line? Should I use a quadratic? You know, what should I use? Again, graph paper in the baskets. Help yourself. Not a problem.
Yeah.